Hey, welcome back to your favorite Fundamentals of College Math class. We're going to take a look at exponential equations today. So far we've had linear growth, right, where we have something with some sort of constant rate of change, and the slope determines the steepness of that. In this section, we're going to look where a quantity grows or decays exponentially. I think it's good to look at a couple examples with some data here initially. So if you notice here, Company A has 100 stores starting out in year zero. Okay, this is Company A right here. So zero, in year zero, they have 100 stores. And then they open 50 new ones every year. So they've got this constant rate of change. So after year one, they'll have 150. 50 more after year two would be 200. 50 more after year three would be 250. Um, Company B, on the other hand, has 100 stores. In year zero, they have 100 stores. So here's Company B data, right? And they increase their number by 50%. So it's a percent increase. So 50% of 100. So they start out with 100, and then 50% more of 100, they'll have 150. And then the next year, they increase by 50% again. So they have 150 from last year, and then 50% of 150, which is 75, ends up being 225. And then the next year they have the 225, and then 50% of that, that's 112.5, so that ends up being 337.5. And let's take a look at these stores in decimals and see if we can make a comparison here. Let me pull up decimals, graphing calculator. Go ahead and get that plus right there and put this in as a table. Let me plot, we do 5 years worth. So this is the first store, Company A. They had 100 to start out, and then they went up by 50 every time. I know you can't see that yet, but I'm going to change my window. And then let me hit that plus again. Do another table this time. This is Company B. Started out with 100, 50% of that, 50% of that added to it. Okay, and then I'm going to go ahead and change this window from let me go from about the x-axis from -5 up to 10 is good. Let me go with y-axis. Let me go like -100. Let me go up to like 1,000. I know we don't go that high, but or maybe let's do like 800. Somewhere in there. Okay. All right. So if you notice, Company A was in green. So and the first two are the same, right? They both have that 0, 100. They both have the one after the first year, 150. And then the green one keeps going like a line. You see that linear growth on that? The blue one, on the other hand, notice it's increasing by 50% each time. So this percent increase, see how it gives some curvature to that? In fact, we'll talk about the equations here in a minute, but let me give you the equation for that. That would end up being this curve right here. I just want you to see that a little bit better. See that curvature on that purple? This is called exponential growth, where you've got the exponential curve on that, right? So that's the difference between linear and exponential, right? So linear, you have a constant rate of change. Exponential, you could have like a percent increase, or maybe a percent decrease would be exponential decay. Um, so here's exponential growth. Exponential decay would look something like that, right? And of course, your lines, your linear lines, are just straight lines that we've talked about. Going here. So exponential growth or decay will be in this. Oops, be in this form. So y equals a times b to the x. Okay, a is this. This is your initial value right here, and the i.e. when x equals 0. So if you think about that for a minute, if x equals 0, a times b to the 0, anything to the 0 power, anything to the 0 power is 1, if you remember. So you see how you end up with a? So that's why that's the initial value, because if x is 0, then b to the 0 is 1, so you just be left with a right there, okay? B is called, this is the growth factor. Now, if b is greater than 1, it'll be exponential growth, but if that number's between 0 and 1, it'll be exponential decay. Okay? Additionally, if we know R is, okay, if it's growth, this a times b to the x, you can find what your percent increase is, because it'll be more than 1, and how much more than 1 is tells you the percent decrease. Whereas for exponential decay, it'll be that b value will be 1 minus r, and you can figure out the r. We'll do some examples here. You'll kind of see that here. All right. So here's your first one. Here's your equation. Y equals 430 times 1.15 to the x. So first of all, you say, well, is this growth or decay? A times b to the x. Your initial value is that 430. In other words, let's do that first. In other words, that's your A. If x is 0, anything to the 0 power, if you punch that in, is 1. So 430 is your initial value. Now, is it exponential growth or decay? So now I'm looking at this b value, the 1.15. Since b is greater than 1, it's going to be exponential growth. Exponential growth on that. And now, what's the rate? Well, since it's bigger than 1, we say, well, this 430, 1.15 to the x, how much bigger than 1 is it? We know this is the form a times b to the x, but let's be specific with that b. It's something more than r, right? Well, how much more than r? If I take that 1.15, I say, well, how much more than r is that? Oh, of course, it's 0.15 is my rate. In other words, r equals 0.15. That's 15/100ths, right? That's 15%. So your growth rate, this is growing at a 15% clip as the units increase. All right, let's keep going with some of these other ones. Next one we got 23 times 0.8 to the x. What's the initial value? Well, it's that 23 right there. It's the a value, because if I let x be 0, I'm left with the a value. I'm left with 23. So that's my initial value, 23. And then secondly, I look at the b. Notice the b is 0.8. Well, since the b is less than 1 greater than 0, this will be exponential decay. Exponential decay. In other words, if you were to graph this, it'd be more like this. It'd be decaying instead of growing there. What's the clip that it's decaying at? Well, if I have something of this form, a times b to the x, and I know it's exponential decay. I'm going to use a times 1 minus r to the x. A 1 minus r. How much less than 1 is it, in other words, right? Your b is 1 minus r here. Well, it's 23 times 0.8 to the x. Well, 1 minus r equals 0.8. Let me get my r over here. And it's 0.2, right? It's 0.2 less than 1. So my rate is 20%. It's decaying 20% year to year. It's decreasing 20% year to year. All right, next one. Now they want the equation. And they say it's exponential growth. A times b to the x. So we know b is greater than 1. We'll be more specific about that. So that's the 1 plus r to the x, right? They give us the initial value, 1.87. I'm going to plug that in. And they give us the rate. It's 5%. So the r is 0.05% per 100. So here's your equation, 1.87, 1.05 to the x. That would be an exponential growth with a growth rate of 5%. Now this last one, let me make a little bit of room here. We've got an initial value in an exponential decay situation. So a times b to the x, but it's exponential decay. Okay, initial value of 52, 1 minus, well, it decays at 10%. R equals 0.10, 10%. So our equation would be 52.9 or 0.90 to the x. That would be the equations. That's how you kind of fill those out on that one. All right, let's continue on here with our examples. T represents the total number of Android smartphones in thousands, smartphone contracts in thousands held by Verizon region, measured in Q quarters since January 1st, 2010. Interpret all parts of the equation. So they've got this T equals 86 times 1.64 squared, all right? So I'm going to go ahead and write this above it, a times b to the x. Now notice b is 1.64, so I know this is exponential growth because it's bigger than 1, right? And I know my a is 86. So let's interpret that first, because we're supposed to interpret each part of this equation. 86 is the initial value. So on 1/1/2010, region had 86. Remember, this is in thousands. So 86,000 contracts, Android contracts, right? Phone contracts. All right, now notice the B is bigger than 1. So this is exponential growth. So what's the R value? How much bigger than 1 is it, right? 1.64 equals 1 plus R. So R equals 0.64, in other words. So this is saying every quarter, this is the time here is in quarters, every quarter the contracts, smartphone contracts, Android smartphone contracts, grow by 64%. Right? That's the growth rate, 64% on that. Okay. Now this value right here, notice they spit it out. 1.64 squared times 86 is 231.3056. So 231.3056 means for quarter 2, so after the second quarter, so they let the QB2 up there. After the second quarter, there were, now remember this is in thousands, so I'm going to times it by 1,000, 231,305.6. So essentially 231,306 contracts. That's what that's saying. All right? All right, let's keep going here with this lecture. Given the statements below, identify which represents exponential equations. Cost of living allowance for state employee increased by 3.1%. So we've got a percentage increase. So this would be our exponential growth, percentage increase. If a value of an investment just goes up by 300 each year, that's a constant rate of change. This is linear, right? That's not exponential. So first one's exponential, second one's linear, so it's not exponential. Third one, tuition costs have increased by a percentage. Again, a percent increase. This will be another exponential. In this case, it's going up, exponential growth. So first and the third one there will be exponential growth. All right, how about this one here? The following equations represent the balance and savings account. Which account grows faster? In other words, whose growth rate is bigger? And which account will have a higher balance after 3 years? So let's look at these. Y equals A1 plus R to the X. So what would our R be? 1 plus R equals 1.05. So your R's got to be 0.05 here. So that your growth rate is 5% on this one. Over here you've got your growth rate 1 plus R equals 1.075. So the R ends up being 0.075 more than 1. So 7.5%. This one was 5%. Right? So which one grows faster? Second one grows faster. Now how about after 3 years? So how much will we have after 3 years? Well, let's plug 3 in. 1.05 to the third. 1.05 to the third. to the third. Enter, so there's that. And then I'm going to multiply it by that times the 1,000 in front. So 1,000 times 1.05 to the third. So it looks like, whoops. So I gotta use this answer button. That answer times 1,000. So it looks like 1157.625. You can do it. This is a pretty nice scientific calculator. You can do it all at once. Just make sure you put in proper notation there. You get the parentheses and the exponent. They'll do it for you. 1157.63, right? The second one was, let's see, I think it was 900 times 1.075 to the third. So that's 1118. So it's actually the first one, even though it grows slower, initially it's got more money after the third year, 1157. Put that down here. So this ends up being 1157.625, so 0.63. This is in dollars. And this one ends up being 1.075 to the third. We ended up getting 1118.067, so 0.07 round that dollars. All right. So who has a higher balance? Well, that one had the higher balance after 3 years. All right, 2008, India's population is 1.14 billion and growing at a rate of 1.34% per year. So growth rate of 0.0134 as a decimal there. Write an exponential equation for India's population, right? It's exponentially growing, A times 1 plus R to the x. And we'll do this in billions. So I can have that A be 1.14 billion, or you could just write it, don't have it be in billions and make it 1,140,000, right? To represent 1,140,000,000. 1 plus R, 0.0134. We'll have this go to time t per year. So 1.14, 1.0134 to the t. Okay, there's our population. Maybe we'll write it in terms of p population here. T years, alright? So what would the population be in 2020? Well, 2008 was, t being 0 was 2008. So 2020 minus 2008, that's 12 years. So let's let t be 12 for the year 2020 and find our population in billions. Puts that in your scientific calculator. 1.337444136. Remember, this is in billions. So in other words, 1,337,441,360 people. Alright. Alright, a couple more here. Bismuth-210 is an isotope. It decays by 13%. So this is exponential decay situations, decaying at 13% each day. Okay. If you begin with, so your initial value 100 milligrams. How much remains after 1 week? After 1 week. Okay, so it's each day. So t is time in days. T is time in days here. So let's go ahead and write our exponential decay. A times b to the x. But we've got 1 minus r, because this is the decay. It's decaying, right? We're initially starting with 100 if time t is 0. 1 minus decaying our 13%. R is 13%, in other words, 0.13. And that's t time in days. So we got y equaling 100, 1 minus 0.13, I got 0.87 times t in days. Okay, here's our model. After 1 week, well, that's 7 days. Let's just plug a 7 in. And we punch that in. 0.87 to 7 times by 100. 47949. Go around in there's 100. 37.73, and this is in milligrams. This is how much is left after a week, right? It's going down by 13% each week on that. All right, last example here. We've got an investment initially worth $10,000. So that's your initial upfront value. Write a formula for this investment for each situation described below. Value increases by 5% every year. Exponential growth equation. T will be our time in years. Okay, we start out with 10,000 bucks, going up by 5% per year. So this is the first one, 10,000, 1.05 times t time in years, right? B, the value increases by 5% every 3 months. Oh, I'm sorry, every 3 years. So let's write that. Every 3 years. Every 3 years. Remember, t is time in years. So after 3 years, if t is 3, you don't want it to go up until then. If t is 3, right? If t is 3, in other words, you want that value to be 1. So what I'm going to do is, that can only go up 5% for every, not too often, only every 3 years. So what I'm going to do is I'm going to take that and divide it by 3. So if you think about that for a minute, oops, missed a 0 there. $10,000, 1.05 to the t over 3. So think about that for a minute. If you put 3 in for t, I have 3 over 3. That's to the 1. Now it's just going up every 3 years. It'll go up 5%. Right? So then the next time it goes up, so when t is 6. 6 divided by 3 is 2. Right? So it'll go up 5%. Second time. And so on. Now, part C says every 6 months. So now I want to double the rate because it does it every twice a year. So I have 10,000 bucks going up 5%, but I got to double that time because it's doing it every 6 months. For example, at the 6 month mark, my time is a half a year, right? 1/2. So if I plug that in, 10,000, oops, 10,000, 1.05 times 2 times a half, t being a half because it's at the 6 month mark. Well, 2 times a half is 1. See that? That's why I make that a 2t right there. Alright, so that's your little introduction to exponential growth, kind of help you get started on that, learn the content. Thanks so much for sticking around. We will see you guys next time.